Okay, here's a quick tutorial on how to approach these Ethernet propagation questions. The first thing you need to understand is that this is the cable. So it runs from here all the way to here. Anything you drop on the wire is immediately going to go in both directions as fast as it can. And at a given moment, it'll make its way left and right a exact same distance. If you let a little more time pass such that this signal has now made its way over to, say, this position, then of course this one will do exactly the same. It will also make its way in the opposite direction. So you can either write down the times here and here and here, or what these diagrams let us do is something a little simpler. They let us say, okay, let's suppose C drops something on the cable at time 0. As long as I tell you the propagation speed, in other words, if I tell you how many time units over here it takes to go the distance from one host to the next, let's suppose I've evenly spaced these out, and instead of telling you how many meters apart they are, I instead just tell you it takes this many time units to go long enough, far enough to get to the next host. Then if I told you it takes 4 to get to the next host, then you know that at time 4, the signal will have traveled to this point, but it also will have traveled to this point, right? So because it travels in both directions at the same time, there's never, ever a circumstance where you drop something on the wire and it only goes in one direction. That's impossible. If you're at the very end of the wire, and most of these standards prevent you from actually being at the very end of at least these shared bus Ethernets, you may not have very far to go, you may not reach anyone, but you're still going to go in both directions. But in this one case, you can ignore this one and just remove it since there's nothing of interest in that direction. So what happens when you reach the end? Nothing. Your signal dies. There's usually a small electronic device there to capture and specifically prevent the reflection of any signal. So your signal gets one shot at it. It goes in both directions at the same time. And what you need to know is the slope of this line, which is basically the same thing as saying, how long does it take to go from one host to the next? All right, so that's one fundamental problem that people have when drawing these things. Sometimes they'll draw them in one direction. Don't do that. If two hosts send something at, let's say, maybe close to the same time, or at the same time, and they make their way across the diagram, and I'm not paying any attention whatsoever to slope right now. I'm being very sloppy with it, although, interestingly enough, it looks like I'm actually drawing it. The one time when I don't care, I actually draw it by accident. Doesn't that figure? Okay, so let's say B starts sending at 0, and of course B is going to send in both directions, and D starts sending at time 1, and D is going to send in both directions as well. Here's your problem, right here. These two signals combine. This is a collision. If you get a question about collision, you've got to show this point. You need to show these two lines intersecting each other. Right? It doesn't do you any good to say A starts sending here and B starts sending here. There's no collision drawn on this diagram. I know there's one right about here, but if you don't draw it, I can't see it. So that's a second common issue that people have with these types of diagrams. And the final one is one that I'm actually lenient on most of the time because it's the hardest one of all of them to kind of fix or to draw, but I'm going to take a stab at it because this is what you saw in all of the examples and in the homework problems as well. Let's say C starts sending, and in our standard, we require that C continues to send bits for a certain amount of time or a certain minimum packet size. Each of those is going to cause more than one bit to enter this network. One bit is going to be flying across the wire, making his way as fast as he can in each direction, while the next bit comes in right behind him, and the next bit comes in right behind them, and so forth. So one way to think about this is that you've got these bits stacked up here, and they're waiting to push their way into this system. So the first bit, second bit, third bit, fourth bit, fifth bit, they're all just stacked up here neatly in this column. And At time 1, the first bit comes out, and it's able to make its way a little bit across the wire. At time 2, what's happening? Well, this bit is no longer here, and the rest of these bits slide down one. Now bit 1 is here, and bit 2 is ready to enter this network and start its journey across. So if you piece these things together and let time go by, what you're going to find is something where bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and so on make their way. But time is passing. So I can't just draw it this way because time is passing. So in fact, bit 1, when bit 1 is here, the second bit is entering up here. And when bit 1 is here, the nth bit is entering up here. So in fact, the right way to draw this thing is to say, I started this diagram up here, and a little bit of time went by, and the path that first bit took keeps getting longer and longer, but it can be basically shown moving down this diagram. So let me try pulling this off, redrawing it. I'm going to show you again. At time 6, let's say, right here, what's going on? Well, the first bit has made its way across to here. Another bit, not quite so far, has made its way across. The bit behind it entered the network. So there's lots of ways of trying to talk this out and draw it. But what you need to eventually get yourself to is something that looks like this. Because the bits that you are dropping on this wire will basically occupy the cable and will grab the attention of the hosts along the way in this realm right here. So if I've dropped my minimum size packet and I've satisfied that requirement, and I finish doing it by time 6, which is what's showing here, then that minimum size packet, of course, takes a little time to propagate across the network. And so at time B, it looks like not that it started at 0 and ended at 6. Maybe at host B, it looks like it started at time 3 and ended at time 9. And A is even further away, so A thinks that the transmission started at 5 and ended at 11. And same thing goes on over here. So that's why we draw these as these chevrons. And if I want to show a different host sending something on the same network here, what I can do is draw something just as tall, right? It's going to make its way all the way across the network. It's also going to look like a chevron, but it's interpreted as having packets here and here and here and here. And there's a collision right here. I can see it because I bothered to draw this whole thing out. I also can ignore these two right-hand pieces if I want, not because they don't happen, but because there's nothing of interest over here. There's no host F. So I'll let you leave those off. They're not really important. Let's try another one. Let's see if we can get another one in here as well. Let's say I tell you you need to send a packet from B for a minimum of 4 sections, and they take 1 time unit to get from one host to the next. So here's what this one's going to look like in this direction. And my drawing's not going to be great here. They do have a line tool, but I'm refusing to use it. We're going to kind of going old school here. So I'm going to continue to draw this thing across. And I'm going to stop there because there's nothing of interest past it. And the same thing here. That one's so bad even I won't, even though I'm being rough here, I'm not going to even do that. So we continue to draw this one here. Right, so that's what this one looks like. Let's say D wants to transmit something. Can D transmit? Yes, D can transmit. D could transmit, say, at times starting at 1. It's the same standard for everyone. If everybody's plugged into a 10 base T cable, everybody has the same minimum packet size, everyone has the same propagation speed, etc. So I could just go down 1, 2, 3, 4. His packet's going to start here, and it's going to continue to here. And I'm going to draw it as if there's no collision yet, because I just want to get good at drawing these things out. And so I can continue on here. And let's see, this one arrives at 4, so it should wrap things up at about 8. So it goes back to B at 7, 6, and then 5. And that makes sense. So here's B's. Here's the collision. Right? So when do people think things are wrapped up? When is the network available again? It's incorrect to say that A thinks it's available here. It's also incorrect to say that A thinks it's available when it first sees a sign of the collision, which would be here. It's only going to think the network's free when nobody is sending anything anymore. And that doesn't happen until down here. Right? So the reason why you want to draw these out as chevrons and not just start them off like a lot of people do with just the first part of the line and you go, that's it, I'm done drawing it. No, you're not. You need to understand the minimum transmission time, and you need to draw it out, because until it reaches these hosts, they don't think the network is available until here, not here or someplace in between. All right, so those are the 4 things. Hope that made sense. I almost made my 10-minute target. It's 11 minutes. So I hope that helps. Bye, everyone.